Hello, I'm Steen Dramlare from the University of Antwerp, and together with my research team, we focus on optimization for machine design. And we explicitly want to show in this presentation that optimization for machine design is something you can do as a machine engineer. We actually want to bring you the feeling, it's maybe an old slogan, but yes we can, or an old European slogan, wir schaffen das. If we look to industry, we see lots of machines like this Netzschroef.
The future is here in
Bolts,
Düsseldorf from 4th to 8th of April 2016. Netzschroef machinery presents At Wire, the Nedform Hybrid, a multi-station metal cold former, uses servo-direct driven technology and mechanical kinematics in perfect harmony. The hybrid technology makes independent and efficient programming of key process parameters possible and results in new forming capabilities, flexibility and high productivity. Visit us at Wire.
We also have that for machines that make brushes or toothbrushes. So what we see for all these machines, custom-made, fast motions, repetitive tasks. They are very common in industry, but also large energy consumption. Actually, the total electricity usage in the European Union, 50% of that goes to electrical motors. So we see large potential there for saving energy costs, but also reducing the carbon footprint. And to do that, we in our research group want to look to the complete driveline. The machine itself has some things we can optimize: the transmission, the motor, the drive, the controller and the motion profile. For all of these we have parts that can be optimized. And so improving the complete driveline means we have to optimize each component. Let's look at the motion profile. This is again the machine that makes fasteners. What we see is the machine needs to move from left to right. The machine designer gives his start and end point, desired start and end point, but the actual motion profile in between, if it's the blue variant or the red variant for the machine manufacturer, that doesn't matter. But it does matter for the energy usage. We see that we can do the same task with a much lower torque, and in essence this means 63% reduction in energy usage of this machine. Machine does completely the same task, the performance is the same, the output for the machine designer is the same, but this can be done with an energy reduction of 63%. The same can be said about more complex machines with more actuators. A default motion for a robot can be optimized into this optimized motion. If we compare these two motions, we also see a reduction of 48.8%. Again, the robot has the same output, but with much lower energy consumption. It does not have to be limited to the motion profile. We can also look to the machine itself. For instance, this is an emergency ventilator, was constructed during the first wave of the corona pandemic. Then we had lots of issues with a possible ventilator shortage. Here this ventilator repetitively presses this back, but we can also optimize dimensions in this machine. And by playing with these dimensions and these mounting positions, we see that we can heavily impact the required torque to drive this machine. And we shown that required torque is directly linked to required energy. And in this case, we were able to reduce the maximum torque by 67%, meaning a 67% smaller motor, and the RMS torque also by 67%, meaning a reduced energy demand. And this was done in simulations, in an optimization that was more or less run overnight. In 14 hours, we had the results. So what I want to show is that the new engineering paradigm is not an engineer that plays with parameters and models this to look if the outcome is okay. Now an optimization algorithm can be used. This optimization algorithm will play with certain design parameters, will put these design parameters into a model, and then will look to the objective value. And based on the response of the objective value to the design parameters, the optimization algorithm repeats this loop to make a better solution. And it's up to the engineer now to set up the model, the optimization algorithm, define the objective, define the design parameters, and define the constraints. This might seem hard, but it is not. First of all, it's important that we define how an optimization problem looks like. An optimization is the act, process, or methodology of finding the inputs that will result in the most effective, best possible outputs given the limitations. So actually, in each optimization problem, we have inputs. These are design variables, things we can play with. We have outputs, that's the objective. That's what you want to minimize or maximize, for instance, the energy usage. And you have constraints, things that have to be kept in check. For instance, the machine has to do the same task. The performance of the machine needs to be the same. That's a constraint. And finally, therefore, we will have the optimization algorithm. Actually, defining these parameters, that's the most important thing. For instance, if you have a bicycle, the geometry will be optimized. These are the design parameters. The objective can be reduced air resistance or increased ride quality, and the constraints are, of course, the strength of the bicycle. If we can define those, we can select an optimization algorithm. And actually, that is the most important step in optimization. If you do it yourselves, first of all, you need insight in what you optimize, and we as machine designers have that insight in the machines. So we need to define the design variables, the objectives, the constraints, and select the optimization algorithm. No black magic required. So this is the optimization workflow, and then we can, for instance, apply this to the machine. Here, this Corona ventilator, we can optimize the lengths, the link lengths, mounting positions. We want to do that to minimize the energy. And we have certain bounds. We have certain bounds on these links at maximum and minimum lengths of these links to be produced. Now, let's take a while to consider the constraints, because beyond the dimension limits we have for our mechanism, not every design is feasible. We have more constraints. For instance, this design cannot be assembled because the link lengths are too short. Or this design can maybe not perform the complete motion. Let me check. And we see that we will run into a singularity here, which makes sure that we cannot do the complete motion. So we have extra constraints. And a very good paper from Le Dijabel had a taxonomy for these constraints. And actually, that's the thing. That's the message I want to give in this presentation. Optimization for machine design or for whatever is not about mathematics. Optimization is about knowing your optimization problem. And that's the thing that we as machine engineers, we have insight in. And we need to use that insight. If you want to do optimization, please do not waste time on lots of mathematics. Please do not waste time on long courses about optimization algorithms. These courses are good, for people that want to develop new optimization algorithms. But we want to use the optimization algorithms. And if you want to use them, you need to know things about your optimization problem. For instance, things like, is your constraint quantifiable or is it non-quantifiable? Can we see for certain constraints it's yes or no, black or white, it's violated or it's not violated, or can we quantify it? Can we relax our constraint, or is it an unrelaxable constraint? Is it a constraint that cannot be violated because otherwise we have no meaningful output? Or is it maybe a constraint that can be violated and can give us some insights? Or is the constraint simulation based? Do we need to run a complete simulation before we know if the constraint is violated? Or can we know a priori before the simulation that that constraint will be violated? And last but not least, is the constraint hidden or known? Some constraints are only revealed by running a simulation. Well, we as machine designers, we as users of optimization algorithms, for us it's best that we know the constraints, that we use our expert knowledge to see beforehand if these constraints will be violated or not. So the preferred scenario is that we have a quantifiable constraint. If it's relaxable or unrelaxable doesn't really matter. That we know the constraint violation a priori before the simulation, and that the constraint is known, that it's not a hidden, unknown constraint. Constraints can be known. Students know when we give this assignment that they can check if the design can be assembled or not. So this is a known constraint. What they sometimes neglect is that a simulation or a mechanism can also run into a singularity. And then for them, it's an unknown constraint. They get no results from the simulation and they think, oh, I ran into a constraint. Of course, we as machine designers, we know that we should take into account these singularities and make sure these constraints are known beforehand. Black or white constraints are not nice. It's good that you know how feasible or how infeasible a design is. And for instance, how do you know if this can be assembled or not? Well, if you pull one of the connection points to the other, we can come in this situation where we can see that the distance at which we cannot pull them together anymore, this is the infeasibility. We pull it towards this point, then we see it's not possible anymore. We have an infeasibility of 50 millimeters. Or in the case you can pull this point beyond point O, then you see that you have a certain feasibility. So we can quantify this, quantifiable constraints. Like this, we see here that for a combination of A, B, and OA, we had degrees of violations. Here, the larger numbers means the constraint is violated to a larger extent. The lower number means we are further away from the infeasibility boundary. And if you can give that information to the algorithm, that can be very beneficial. Here we see this again, a top view. So we see here a constraint that is quantifiable, very interesting. We see the constraint is violated further, and then a little bit less. We cannot relax this constraint. If we cannot construct a machine, we have no meaningful output. We run a simulation to know if this constraint is violated or not, and it's a known constraint. We know it beforehand. And so we now know that this is the feasible design region. That's important. You can run your optimization algorithm without knowing that, but if you use your expert knowledge in your optimization algorithm, you will win a lot of time. Maybe a machine designer wants to limit material use, so the sum of the both lengths of axes have to be limited. This is an extra constraint. The question is, however, does this really have to be a constraint? You can relax this constraint. If you go beyond the constraint, you can still know the value. Your simulation can still give you valuable results. So this is a quantifiable, relaxable, a priori known constraint. And then a little word about constraints knowing a priori or in simulation. And this again corresponds to my title. to perform machine design optimization in our group, we want to do things that are really applicable for small and medium enterprises, for machine builders that do not have the mathematical insight. Yes, the things I've shown, like feasibility to construct your mechanism, or the things I've shown on singularities, well, experts, academics can write down the formulas that will exactly define if it's feasible or infeasible, if we're in the feasible region, the infeasible region, or at the feasibility boundaries. That's correct. We can do that, yes. But a machine designer does not necessarily want to get involved in all these mathematics. And the nice thing is that these simulations can also quantify your constraint, can also tell you if it's feasible or infeasible. It's better to know this a priori. Your optimization will run quicker, but if you don't know it a priori, then your simulation might also give you these results. So yes, it's preferred to know it a priori, but know that you can also harness the power of the simulation. So now we already said a lot of things. I want to tell a little bit more about these models. It's important in the optimization workflow that we have a model that mimics reality. And again, machine designers, engineers that want to run optimizations, it's not here that we should put effort in. It's not by going in depth in mathematics that we will be able to harness the power of the optimization. Our strength lies in modeling what we want to build. If we have a model, we can optimize. And the optimization algorithm should just bring the design parameters. We should define our constraints, try to know them, try to quantify them, try to have a clear view on them, and then the model can transfer the design parameters into an objective value. And of course, I already made the distinction between the analytical and the CAD models or any simulation models. An analytical model is complex for many users. A simulation model can be much easier. But an analytical model will run very quickly, and a CAD model will sometimes take time, or a simulation will take time. And we saw this loop where the optimization algorithm will repetitively give new design parameters to your algorithm. So can we combine both methods? Why would we combine it? Well, the optimization algorithm, for instance here in motion profile optimization, will give design parameters to the model. The model will determine the objective, and we will have a loop here. A loop that will be run repetitively. The optimization algorithm will piece by piece, step by step, define new design parameters to find the best objective value. So it means we have to run this system model multiple times. And therefore, it might be good that we have a model that is quick enough, that we can run this model quick enough. Therefore, what we do in our research is we try to feed an analytical model with information from the CAD model. That's the best of both worlds, especially for machine designers. They can use their simulation environment, the environment they know. They draw their machines in CAD models, in PTC Creo, in Siemens NX, in lots of other CAD packages, Inventor, etc. But if we can in some way extract data from this CAD model to a formula, then we can combine best of both worlds. And that's what we want to do in our research group. Is for the machine designer, we don't want the machine designer to get involved with formulas. We want the interface to the user, a CAD model. And then with the right extractions, we have publications on that, and I will show you the links to those at the end of the presentation. Then we can run and we can rely on this approach. All right, knowing all this, we come to the algorithms. You see, algorithms are not at the beginning. They're not that important for us. We just need to know which one to use. about these algorithms. There are many options for these algorithms. You only need to use them, you only need to select them, but I want to make a distinction. We have gradient-based algorithms, gradient-free algorithms, and global algorithms. Let me go through them. Not to learn you how to program them yourselves. I would not advise doing that. I would advise just using an algorithm, just using a toolbox, but it's important to select the right one. The gradient-based algorithm, most common one, we have an objective value, we have a design parameter on the x-axis. The algorithm knows nothing in advance. It just starts from a certain feasible design. And then it looks to the gradient, where the gradient is descending. That's the good direction to look for an objective that is as low as possible. And then whenever it sees an increasing gradient, it knows, okay, we passed the lowest point. This will be the optimum. In practice, the curve can look like this, but it's very important. An optimization algorithm does not know this. An optimization algorithm runs repetitively your model, being it analytical, being simulation, gives design parameters and check what is the value of the design parameter. And what we see here is that these gradient-based algorithms can get stuck in a so-called local minimum. This is, of course, the option, the design you want to select. This is the global minimum. But a gradient-based algorithm just takes a decreasing gradient. Whenever it sees the gradient increases, it stops because it knows there was the lowest point. I want to stick to that lowest point. This is simple because it's 1D, it's only one design parameter. In practice, we will have more design parameters. We already know our feasible design region for this machine design optimization. We start at the feasibility boundary and we see here a value of 7.92 Newton meters RMS. And again, the algorithm takes gradients, walks along the steepest descent of the gradient, and in that way finds an optimum. So we saw that it finds a way to the optimum, but we also know by now that these gradient-based algorithms can get stuck in a local minima. Maybe there's a better position over here, maybe there's a better position over there. The gradient-based algorithm will only look to the values it sees along the steepest descent. And whenever it increases, the gradient-based algorithm stops. So actually, we might never explore this area where maybe the optimum is better. Maybe the global optimum is over there. Gradient-free algorithms, well, if you don't have a mathematical formula, then it might be difficult to calculate a gradient. So if it's difficult to calculate the gradient, it might be good to just take samples in a smart way, more or less like the gradient descent, but without the gradient. And in that way, for instance, a simplex algorithm just mirrors a point along two other points to also find the steepest descent, always takes 3 samples into account, and in that way, in a deterministic way, will always end up in a minimum. If you start from a certain position, you will always end up in the same position with these so-called deterministic algorithms. A pattern search is also more or less the same. You take, in this example, 4 samples, you walk along the lowest sample, maybe you also decrease the step size, and in that way you can find the optimum. Good algorithms, fast algorithms, but they can get stuck in a local minimum. If we want to avoid getting stuck in a local minimum, we have things like a particle swarm. Particle swarm like a swarm of bees or insects, or a genetic algorithm that goes step by step. This algorithm is based on multiple generations. It takes the offspring of the best value and then does mutations, crossovers, etc. Again, I promised you no black magic, so I won't get in depth of the mathematics. But the thing of these algorithms is that they, in some way, keep on exploring the complete design space. They don't necessarily go along the steepest descent. They take multiple things into account. They also, of course, take into account the best values, but they still try to explore the complete design space to avoid getting stuck in a local minimum. They don't get stuck in a local minimum, but they're not deterministic. If you run them 2 times, they can end up with a different optimum, because there are certain random nestings in these algorithms. And these random nestings are good, because based on these random nestings, the algorithms keep on exploring the complete design space. And yeah, I told you there are many optimization algorithms, and I have the impression that lots of people are intrigued by the particle swarm, because if you look in literature, you see border collie optimization, whale optimization, chicken swarm optimization. I actually sometimes think that there is no animal of which there's already an optimization algorithm. Well, if we have a global optimum, then, of course, we want to find the global optimum. That is the best value. Sometimes people say to me, yeah, it's not optimization if you get stuck in a local optimum because you want to find the best solution. Yes, you do. And then we might say, why not just always use a global optimization algorithm? Well, because one does not simply find the global optimum. To find the global optimum and to guarantee that you find the global optimum, it's very difficult. You see, for instance, in MATLAB, the global optimization toolbox lists the genetic algorithm particle swarm optimization. These have some randomness. This randomness can in some way help you to avoid getting stuck in a local optimum, but there's heuristic, and they cannot guarantee that you find the global optimum. I call these algorithms illusionary global. It gives you the illusion of, yes, we might not get stuck in a local minimum. They can find the global optimum, but it's an illusion. You're not sure. We have the estimated global optimum. This is a technique, the Gaussian process and Bayesian optimization, that gets lots of attention recently. It's very interesting. On the one hand, a Gaussian process or another surrogate model will be used to make a model based on the points you already observed. And based on those already observed points, you will have a model that will predict the mean value and that will also predict the standard deviation around this mean value. And in that way, we might see, okay, based on these sampled points, the blue ones, based on the predicted mean, based on the predicted uncertainty, standard deviation, we might see that this is the most interesting point to poll the next. And if we do that again, we polled this point. So only the points indicated here are actually known because we run a simulation on that. The rest is just a model predicting the mean, predicting the standard deviation. And with this prediction, you can also predict or say this would be the most interesting sample to sample the next. By doing so, this algorithm gives you a so-called expected improvement. It's a very interesting parameter because that expected improvement says, based on the mathematics behind this, based on the statistics behind this, we expect that if we keep on running the algorithm, the next value might be, for instance, 10 Newton meters better. If the expected improvement is 10 Newton meters, you for sure will keep on running the algorithm because, 10 Newton meters is significant in many cases. If your expected improvement is only 0.0001 Newton meters, then you might say, okay, maybe we're in a local optimum, but if the expected improvement is limited to 0.0001 Newton meters, that global optimum might only be 0.0001 Newton meters better, then I can settle for the local optimum. However, this is not a hard boundary. It's an estimation. It's an estimation of the potential deviation. We have to be very careful with the wording here. The expected improvement is not a strict bound on the difference between the current and the global optimum. But, and we can go on further, for every design parameter set that was not polled, there's a non-zero chance that the objective is out of the confidence bound. So this does not guarantee you the global optimum, but it gives you some estimation. It gives you some kind of feeling of how much better it could be. We could say this. We have an even better alternative. That's the deterministic global optimization. Interval optimization is capable of exactly saying where the global optimum is. That's the only algorithm I know about that gives you guarantees. The disadvantage is you need a formula. Interval optimization determines bounds, and you see bounds on the expected maximum and minimum value. You see here, based on all the intervals we already had, the expected maximum of this one is the lowest. We draw a line here, and all the expected minima here are beyond that maximum, so we can all neglect these squares and limit ourselves to these regions and start making extra intervals. Very nice algorithm, but this deterministic global takes lots of time, has a low application range, can handle different problems, but we need a function. The gradient-based algorithms are just the opposite, go very fast, cannot guarantee global optimum. The application range is sometimes also limited because we need to be able to determine the gradient, and they need a smooth objective, so it's advised to use a function. The deterministic gradient-free algorithms, they are a little bit slower but have a larger application range, don't need smooth objectives, don't need functions. The gradient-free heuristic, the global illusionary algorithms, the genetic algorithm for instance, is slower, has the highest application range, doesn't need smooth objectives, doesn't need a function, but has a high tuning impact. And the the Gaussian process Bayesian optimization, the new kid on the block, there's lots of buzz around that. QuaSpeed, it's quite good. It has quite good application range, but we cannot guarantee the global optimum, but we have some estimation. Little word on multi-objective optimization. Sometimes you want to optimize complementary objectives, cost and material minimization. You can put them in a performance function, which is the weighted sum of both objectives. But sometimes you have competing objectives, strength and material. The more material you allow, the better the strength can be. You have certain dots that give you the original situation. Thanks to an optimization, you can optimize the strength for a given amount of material. But this so-called Pareto front you will obtain, which will clearly show you that this is the optimal point, the best material strength ratio. It doesn't make sense to add more material. Putting up this Pareto front takes lots of simulations. So you have to wonder, do I really need both objectives? Always consider maybe one of your objectives as a constraint. In fact, it would seem perfectly logic that the strength is a constraint. You need a minimum strength, and the only thing you have to optimize is the material. If the values are complementary, why not just picking one? Every time you have multiple objectives, think if you need them, both or all three of them, and think if maybe you can convert one objective into a constraint. It will save you lots of time. So, in conclusion, don't waste time on the mathematics of optimization. This is what you need to know. Select your design parameters, your constraints, your objective value, the model you use, and the optimization algorithm. And in selecting the optimization algorithm, you're the customer, not the producer. Just pick one that suits your needs. Do you really need more than one objective value? Can you convert one of them into constraints? You can run models in simulation or transform maybe to equations. That's a good practice if it's possible. Your best constraint is a known constraint that you can define a priori and that you can quantify. All right, thank you very much for your attention.